Hello guys, welcome to homework number 22. I will go straight ahead now to share the problems for this homework. So the first question says focus on concept. Question 01. A conducting rod is moving through a magnetic field. As in the drawing, the magnetic field strength is 0.65 Tesla and the speed of the rod is 5.4 meters per second. Suddenly the field strength decreases to 0.48 Tesla. To what value must the speed V of the rod be adjusted to reestablish the EMF induced between the ends of the rod at its initial value? So our EMF induced is BVL. So we have the magnetic field initially to be 0.65 times the velocity, the speed is given to be this. So the length stays the same. So we just put L for the length. We are not giving what the length is. So it's 3.51 L volts as the induced EMF. But now we want to keep every other thing constant. The length stays the same, but we are changing the B field to 0.48. And they're asking us to get the speed that we will have to make this induced EMF the same. So I equate 3.51 L volts from the first B. Then I multiply the new B by a new V times L again. So the L's cancel out. So my speed becomes 3.51 divided by 0.48. 7.3125 meters per second. That becomes the answer to this problem. So we'll go to the next problem. Focus on concept question 06. It says, in a certain time period, a coil of wire is rotated from one orientation to another with respect to a uniform 0.38 Tesla magnetic field. The EMF induced in the coil is 5.6 volts. Other things being equal, what would the induced EMF be if the field had a magnitude of 0.55 Tesla? So again, other things being equal, EMF induced is minus number of turns, change in the flux, magnetic flux over change in time. So the magnetic flux is magnetic field times area cosine the angle minus magnetic field times area cosine the initial angle. So this is the difference. So we just gonna keep all this constant except the magnetic field. So we have NBA cosine all this, so it's just B. So E induced is just B times some constant. Is that okay? So E induced over B is all constant. So this E induced divided by this B is all constant. So I'm just working with this formula. We are not giving psi, we are not giving A, but we are keeping all those constant. So the only things we are changing is the electric field, the induced EMF and the B field. So we have an old EMF given, 5.6 volts, and the old magnetic field that gave that EMF is 0.38. So from there we get the constant. So these are all constant. Now we are going to get a new induced EMF giving a new B field. So what is the new induced EMF if we change the B field to 0.55? So I put my B to be 0.55, I get a different EMF. The constant stays the same. So it becomes 14.737, which is our constant, times 0.55. This becomes the new induced EMF. Okay. So I go to focus on concept question 07. It says the drawing shows 3 flat coils, 1 square and 2 rectangular, each being pushed into a region where there is a uniform magnetic field directed into the screen. Outside of this region, the magnetic field is 0. In each case, the magnetic field within the region has the same magnitude, and the coil is being pushed at the same velocity. Each coil begins with one side just at the edge of the field region. Consider the magnitude of the average EMF induced as each coil is pushed from the starting position shown in the drawing until the coil is just completely within the field. So rank the magnitude of the average EMF in descending order. So we're going to start from the largest to the lowest. So this is what we have. Induced EMF is negative d phi dt with number of turns if you have more than, but this is just one turn. They are just one flat wires. So that's why you don't see the N here. So phi is the magnetic flux, which is magnetic field times area. So, but we have a constant magnetic field going into the screen. So I bring the constant out, so it's going to be dA over dt. So what is changing now is the area as you move. So as the area is changing, only one side is changing in length with time as it is entering the field. This horizontal part is the one that's changing with time. This vertical side stays the same. So this one is constant. This one is the one that changes after 1 second, this part, after 2 seconds, this part has entered. After 3 seconds, it goes deeper. After 4 seconds, like that, just for instance, for example. So now what we are going to do is how does this dA change? So EMF induced is proportional to how the area change. But how does the area change for the first one? It has LL. So it's just L. This side is also L. So that is the constant L. This DL is this charge that changed, which is also L. So that is the DL. Let's go to the second one, you understand. For the second one, dA changes at 2L is constant. So there is no D in front of 2L. But L is the one that's changing as we are going in. So it's 2L DL. Then for the third one, L is constant right here. For this third one, the C part, L is constant, and we have 2L changing right here. Is that okay? We have 2L changing. Okay. Okay. So what we're going to have here now is the largest one is going to be B. Okay. Followed by A and C are the same. Yeah, because this 2L is the whole length. So don't confuse this 2L, the whole length. This 2L that is the whole length is not going in at once. So it still changes as DL. Is that okay? It only becomes 2L at the end when everything goes in. So it's still going to change as DL, basically. So 1 and 3 are going to be the same. That's A and C are going to be the same. But B, this second one, is going to be the highest one with 2L constant. Okay, with 2L staying constant. Okay. Now we have focus on concept question 08. It says a long vertical straight wire carries a current I. The wire is perpendicular to the plane. So you know when you have current carrying wire, you use your right hand rule. The current is in the thumb. The magnetic field is like this. So the magnetic field will flow around the wire. So when a magnetic field is around the wire, then you can't produce current in the same wire because you have to produce current outside. Okay? So in that case, there is no induced current at all. So another way to say that is the magnetic field and the area you're supposed to produce the current as this thing falls down is inclined at 90 degrees. So cosine 90 will give you 0 for the induced EMF. Okay, so that's one way to look at this problem. Okay, so the loop is allowed to fall and maintains its orientation with respect to the straight wire while doing so. In what direction does the current induced in the loop flow? There is no current induced at all in this case. Okay. So chapter 22, problem 001 says 0.61 meter aluminum bar is held with its length parallel to the east-west direction. So you can see the east-west direction. So we're looking at this from the top. Before the bar hits the river below. So it drops from a bridge. And just before the bar hits the river below, its speed is 23 meters per second. And the EMF induced across its length is this. So you're looking from the top, is falling down to the river. That's the diagram you see here. So it says, assuming the horizontal component of the Earth's magnetic field at the location of the bar points directly north. So this is what we have, the Earth's magnetic field. Determine the magnitude and, of the horizontal component of the Earth's magnetic field. Is that okay? So we want to find B. So B is just, induced EMF is BVL. So B is EMF over VL. So EMF is given in volts, the velocity is given, and the length is given. So that's the magnitude. So we want to see whether the east end or the west end of the bar is positive. So now we're going to do the coil. Okay, is that okay? So we're going to do V cross B. So what is V cross B? So V is going straight down. The velocity is going into the page, and B is going up. So when I do into the page, I'm going up V cross B. I'll be scrolling out to the right. So it's going to be east. So, and that direction is for positive charges. Negative charges are going to go in opposite direction. So positive charges, the side of the bar that's positive will be the east side. And the west side will be negative. So because that's the side protons will go. The side that coincides with our call, V cross B. Okay. Chapter 22, problem 3 says, in 1996, NASA performed an experiment called the Tethered Satellite Experiment, in which, in this experiment, a 2.15 times 10 per 4-meter length of wire was let out by the Space Shuttle Atlantis to generate emotional EMF. So the shuttle had an orbital speed. So the speed is given and the magnetic field is given. You are just asked to find the motional EMF. So motional EMF is just VBL, speed times magnetic field times length. And that's straightforward for this problem. So the same thing for the next problem. You can see here, all you need to do is get the B, get the V, and get the get the L. Is that okay? That's given, which is the diameter in this case. So you're going to say BVL for this. This is chapter 22, problem 04. So we are seeing the magnitude of the voltage that is measured with electrodes in the drawing. So the voltage that's going to be measured is the induced EMF, which is this. Okay. Now, chapter 22, problem 05. So this is drawing showing 3 identical rods, ABC, moving in different planes. So you can see A going like this, B going like that, C going like that. This is X, Y, Z. A constant magnetic field of magnitude 0.59 Tesla is directed along the Y-axis. And the length of each rod is given and the speeds are the same. Find the magnitude of the motional EMF for each rod. Is that okay? So for motional EMF for rod A is 0, as you can see here for this rod A, because the velocity of the rod is parallel to the direction of the magnetic field. Okay. Okay. And the charges do not experience any magnetic force except the motion and the field are perpendicular. So then the motional EMF for rod B, according to the VBL equation, is just V times B times L. So you get that. And then the positive end of rod B is going to be V cross B for rod B. So V is going up, B is going to the right. So V cross B will be going towards inside. So that's the end 2. That's where the positive charges are going to be. Then the motional EMF for C is 0 because magnetic force on each charge is directed perpendicular to the length of the rod. So for the ends of the rod to become charged, so the magnetic force must be directed parallel to the length of the rod. So this one is also 0 for the C part. Okay. So now let's see chapter 22, problem 13. In this case, we are given an initial angle, and then that initial angle at 0 is our phi max. So it's going to be the maximum magnetic flux, which is BA cosine 0, which is just BA. So they're asking us to find when the flux decreases from its maximum value to 1/6 of its maximum value. So we are looking for BA cosine phi 2 such that it gives us 1/6 the maximum value, which is BA. So the maximum is when 0, you have 0 angle cosine 0 is 1. So how do we get 1/6 of BA? What angle gives us that? So that's what we're doing right here. So BA cosine phi 2 equals 1/6 BA. So cosine phi 2 is 1/6. So from here, we just find the psi angle corresponding. So this psi that is in italics is angle, and this uppercase psi that is quite larger is the magnetic flux. So don't confuse both. Okay. Okay. Chapter 22, problem 44, very easy. So here we have a back EMF that is given, and we have the volt socket. So the difference from the volt and the back EMF divided by current, it gives you a resistance. That's how we solve this problem 44. Okay. And then for problem 45, this is motional EMF, mutual inductance problem that we've done in recitation. So induce the EMF induced in one coil is the mutual inductance times change in current over change in time. So from here, we find our mutual inductance to be this. So we always take the difference from 0 to where it gets. That's actually what cancels the negative sign, if you like. Okay. So then we get this. That's our mutual inductance. So this is induced EMF, this is time, and this is current, changing current. So chapter 22, problem 60. So this is talking about step-down transformer with turns, ratio 1 to 45. So turns ratio is number of secondary over number of primary turns. Okay. Okay. So the voltage is given to be 120 volts. That's the primary voltage. Okay. So they are looking for the secondary voltage. So we use this. Voltage in secondary over voltage in primary is number of turns in secondary over number of turns in primary. From here, we'll find voltage in secondary, and that's just straightforward. And then the last problem, chapter 22, problem 61 is the same thing, but this time around, the current is inverse. So current in secondary over current in primary is number of turns in primary over number of turns in secondary. So this is what you need to do this. So from here, we have the power to be current times voltage, okay? So what is current right here? So current right here from this one is IS NS over NP from 22.13. Then put this here. So power becomes I primary, V primary. Instead of I primary, I have IS NS over NP, then times VP. And I put everything there. This I in secondary times number of turns in secondary over number of turns in primary times voltage in primary. That gives us the power that we have there. And that is the end of this homework. I'll see you guys next week and have a good one. Thank you.